Well, thank you all for joining another lecture for Introduction to Computer Graphics. So I'll jump in and start talking about today's topic. And today's topic is going to be, big surprise, shading. Yeah, we're going to talk about shading. So, what is shading? Those of you who have done some computer graphics stuff before have some idea, maybe. But when you think about shading, when I ask people like, what is shading? Like, what are you talking about? Like pencil shading? Like something like this? This is shading. This is literally shading. So, different types of shading with pencil, right? So what we're going to do in computer graphics is actually going to be very similar to this. It's going to be a very similar concept. But of course, we're not going to be doing it with pencil. We're going to be doing it on 3D models. It's going to be all about computing color and color variation on 3D surfaces. Not necessarily 3D surfaces, but yeah, that's where we're going to start. So, shading in computer graphics. If I have this lovely teapot, what a lovely teapot, isn't it? It's a little too dark for my taste. So let's put some color on this. I'm not digging this black so much. Let's make it red. How about that? Kind of fits the overall theme here, right? Red teapot. Great looking teapot, isn't it? Now, not so much. It's a little flat, don't you think? It doesn't look like a 3D teapot to me. It's pretty flat because it's the same red everywhere. I mean, I would expect to see something more like this, right? With some color variation. Some parts are darker, other parts are brighter. And then this finally looks 3D. And that's very, very important. That's what we're trying to do in computer graphics, right? So, what's going on here? This whole thing is about light, right? And this whole thing is about lighting. So a lot of the conversations that we're going to have regarding shading is going to be actually about lighting and how to compute light reflectance of surfaces. Because based on that light reflectance, we're going to have some parts of the object that's going to be dark and some parts of the object that's going to be bright. So you may or may not have paid attention to how things look like in the real world and what parts of objects are darker and what parts of objects are brighter. But you all have a very good intuition about how light works. Even if you haven't ever thought about this, you have a very good intuition. And you can tell by looking at this, it's like, probably there's light above, right? Even if you don't think about this too much, you can tell by looking at this image, you can infer the 3D shape of this object because your brain is sort of wired to understand this lighting. And just from this lighting and from this let's call it shading, you can actually tell the 3D structure. So getting this lighting and light reflectance of the objects right is very, very important. So we're going to talk about some basics of that whole procedure today as a part of our discussion on shading. So let's do that. But let's not start with teapot right away. Let's start with something a little bit simpler, a flat plane. How about that? Now again, this flat plane looks dark because I don't have light yet. So if I just put a light on top of this, we'll finally see its color. Yeah, it was red, but we couldn't see that it was red because there was no lights. So when we have light, we can see that it's red. Now, this light is coming from, I just put a light figure here just to show you that there is light above here. But don't think about this as like an actual light source or anything. It's just some light is coming from above. That's what I'm trying to say here, right? And so let's say that this is my light direction. My light direction is towards up, and I'm going to represent my light direction with this omega symbol here. Omega is going to tell me where the light is coming from. In this case, this light is coming from above, right? So if I take this plane and I rotate it, what's going to happen? If I rotate it a little bit, it's getting a little bit darker, you see? It's getting a little bit darker. See, my light direction is still up, but I rotated my plane. I'm going to rotate it some more such that it's almost in the same plane as my light direction. It's almost black now. It's not quite black, it's still reddish, but it's almost black. And if I rotate it a little bit further, now the light is sort of on the back side. Now it's completely pitch black, right? And I can rotate it a little further. Yeah, see, it's completely black on this side because light is coming from the other side of the surface. From this side, there's no light coming in, so it's black on this side. So if I rotate it back, and still black. If I rotate some more, and now I'm starting to get some light on the surface, and I rotate it all the way back. Now I'm fully getting some light on the surface, and I'm getting its full color. So let's see what's going on here and why this is happening, so we can actually quantify exactly what's happening here. So for that, I'm going to do a different view. So let's look at it from this cross-section view. And for that, I'm going to look at a beam of light coming from this light source, right? A beam of light just coming and hitting this surface. So in this case, this beam of light is eliminating a portion of my surface here, like this portion. That this light beam fell on this surface and it eliminated this portion, all right? And in this case, in this specific case, my light direction, omega, is the same as my surface normal. So my surface normal is perfectly aligned with the light direction. Right? So you can say that the light direction is perpendicular to this plane. All right, everything's good? All right, so what I'm going to do here is that I'm going to take this plane, I'm going to start rotating it. I'm going to rotate it this way now. Let me rotate it just a little bit. You see now the surface normal is not aligned with my light direction. It just moved a little bit. Let me rotate it some more so you can actually see the difference. You know what? I'm going to rotate it even more. All right, over here, there's quite a bit of difference. Here's what happened. This light beam that eliminated this small area on the surface, now it's spread to a larger area on the surface. It's the same light beam, but now it's spread over a larger area on that surface, right? And it all depends on, it's all based on the angle between this light direction and the surface normal. Let's call it theta. Theta is the angle between the light direction and the surface normal, right? So let's investigate what's going on here. For that, I'm going to move this side. I'm going to zoom in a little bit so we have more space to work with. Just gonna zoom in. It's still the same light beam. So before I rotated this plane, it was flat like this, right? And let's say the length that in this 2D cross section, the length that my light beam covered, let's call it unit 1. So that my light beam was eliminating some length that was, let's say, call it 1 unit. All right. After I rotated it, now it's spread over a larger area. Let's give it something. Let's call it S. Now that I rotated it, it's spread over an area that's as long as S. So if the light per unit area here, the light illumination, light per unit area in this case was, let's say, L. If it was L, after I rotate it, now it's spread over a larger area by S. So after I rotate it, it's going to be L over S, right? So this was L over 1, which was L. Now it's going to be L over S because it's spread over a larger area. So that's why when I rotate it, I will expect this to look darker now because it's receiving less light per area. Does that make sense? Because S is greater than 1, obviously. Now, but how much greater than 1? Can we exactly say how much it is based on this angle theta over here? Because that's going to determine everything, right? So if that angle is theta, this angle is going to be pi over 2 minus theta, right? Because light direction was perpendicular to the plane, so this has to be pi over 2 minus theta. And this is pi over 2 minus theta. This remaining angle here must be theta because my surface normal is perpendicular to the plane. right? All right. So based on this, can I form a relationship between, that tells me what S might be? Yeah, that's going to be about cosine theta. So what is cosine theta? Cosine theta is going to be, like, this is a right triangle, right? So it's going to be this length, which is 1 over the hypotenuse, that's going to be 1 over S. All good? And if cosine theta is 1 over S, and I want to get this quantity, that quantity becomes L cosine theta. All right? So from this, I can see that the amount of light I receive on the surface scales based on cosine theta. So that's going to determine the amount of light per unit area that I'm going to get on the surface, this cosine theta. And we call this cosine theta the geometry term. And that's going to show up in our shading equations and much later too. And this geometry term is going to determine how much light I'm receiving per area on the surface of my material. That's why it's very, very important. And it's purely based on the geometric relationship between the light direction and the orientation of the surface. Right? That's why we call it the geometry term. It has nothing to do with what kind of surface, like what's the color of the surface. I don't care. That's not what we're talking about. It's just about what percentage of the light, how much the light is scaled based on the geometric orientation. So this is the geometry term, right? And I'm going to repeat this again. This cosine theta is the geometry term. It's going to come up many times. When I say geometry term, I would like you to understand that I'm talking about this cosine theta. Okay? All good? All right, let's move on. Let's get back to 3D again. So here's our plane, and in this case, the light direction and the surface normal is aligned. Now, instead of rotating this plane, this time I'm just going to move the light source. I'm going to get the light from a different direction, so move the light source. See, it got darker. Did you see that? Did you see that? So it was brighter over here, and it got darker. How lovely is it? All right, and it all depends on this angle between the surface normal and the light direction. Now, I said this was red. How did I do that? Well, I had to, specify that. I said that my material, this material on this surface, was red. So let's give it some name. Let's say KD, for reasons why that will be a little more clear later on. I'm going to call this KD for now. And this was red, and you see it's not the same shade of red now. This is a little bit darker. It's a little bit darker because light is coming from an angle. So what I see here is more like KD times cosine theta, KD times the geometry term. All right. So to be able to figure out this color that I'm supposed to see on the surface, I need to compute this cosine theta term. Now, presumably, I know the light direction. I should know the light direction, and I should know the surface normal. So, and this KD must be given to me, and I should be able to compute this cosine theta, KD times cosine theta. And that would be very easy. Can you compute the angle, cosine of the angle between two vectors? Very, very easy, especially if these are unit vectors. Yes, exactly. That's going to be the dot product. So the dot product of n and w, the order does not matter because it's dot product. This is going to give us cosine theta, the cosine of the angle between them. And this is a very, very important identity. We're going to be using that a lot. This is very, very important. Now, this only works because both of these are unit vectors, right? They have to be unit vectors. If they're not unit vectors, then dot product is going to be scaled by the length of the vectors. So yeah, they're supposed to be unit vectors such that we get cosine theta. Now, I can do this, right? So if my surface color is red, then I just multiply it by the geometry term, and I get the proper shading color of the surface that I'm supposed to see. All right. What if I'm using a texture on this surface? What do I do then? Things are getting a little bit complicated. I don't have just one color. I have a range of colors based on the texture, right? Now, in that case, the texture is going to be my color, right? So my color is going to come from this texture. So my KD is not red, my KD is whatever the texture is. Whatever the texture value is at that point on the surface, all right? So I'm just going to sample the texture on the point that I'm trying to shade, and I'm going to multiply that color by the geometry term. Another thing that I haven't considered here is the intensity of this light, right? I mean, the light intensity is going to have some value. Like if the light is kind of not very strong, things are going to look dark, obviously, right? If I have very strong light, then things are going to start to look really, really bright. So yeah, there's this geometry term, yes, but things also depend on this light intensity term, right? And it's not just the magnitude of intensity. Light sources can have colors, right? If this light source is tinted in some way, I'm going to see that tint on the surface as well, right? I mean, you've all seen this. If you have colored light source on a material, you're going to see that color on the material, right? So the color that I'm going to be seeing on the pixel color, is going to depend on all of these terms. The light, this is a color term, light intensity, including its color, multiplied by the geometry term, multiplied by my surface color, right? And this type of material is what we call a Lambertian material or diffuse material. So this D came from diffuse. This is the diffuse coefficient. That's why I'm calling it KD. And this is a color value, but it can come from a texture. And this is the color or intensity of my light source, and this is the geometry term. And if when you multiply them all together, I'm going to get the final pixel color that I'm supposed to see. All right. So when we're doing shading with a Lambertian diffuse material, this is going to be the equation that we will be using, and we're going to get different variations of the surface color based on this equation. It's going to be purely based on the geometry term and, of course, material property and the light source. So here is an example Lambertian material on our lovely teapot. In this case, I'm using a more reasonable texture on the teapot. So now we have a wooden teapot, right? So this is what a Lambertian material would look like. Looks fine, right? I have parts that are darker, parts that are brighter. Actually, the lighting here is a little bit complicated. So if you're trying to see where the light is coming from, and if you can't, this is understandable because for eliminating this, I'm using multiple light sources, not just one. Light is coming from in multiple places. But you can still see some color variation here. Like, so the bottom over here is a little bit darker, and over down here is a little bit darker. So you still have enough information to tell what this shape looks like. Now the thing about this material is that it's a little dull. So it's like a wooden teapot that's not polished, right? It's kind of rough. It's not a very smooth and shiny surface. Because if it was a smooth and shiny surface, it will look more like this. Now this one looks shiny, right? So if I rotate both of them, you'll see that this one is shiny. This one is kind of dull. Now this one, the one above, is just diffuse only. It's a Lambertian material. It only has diffuse type of reflections on the surface. So light reflects diffusely, as we call it. So the other one has what we call specular reflections on that, and these specular reflections is what gives it this shiny look to it. All right, and so that's very important to do. Let's see how we can get shiny objects and shiny materials. Now, These specular reflections, you can think of these specular reflections as the reflections of our light source. Right? So if I move this light source from certain angles, I might start seeing the reflections of the light source. And that's exactly what these specular reflections are. So if I move this a little further, you'll see that these reflections are going to be somewhere else. These specular reflections are going to be somewhere else. And they will move as I move my object or as I move the light source. So you will just sort of dance around on the object. So unlike the diffuse component, diffuse reflections that are sort of attached to the surface, right? So there was the surface color. It was either we put a brick texture or we put a wood texture. They were attached to the surface. But these specular reflections are not they don't look like they're attached to the surface. They sort of move around as I move the light source, right? They're almost moving with the light source. Right? So if you look at these teapots, you see that the specular reflections on this teapot are sort of moving around, right? I mean, they're kind of like staying exactly where they are, and the teapot is rotating. That's what it looks like. But on the teapot, they're moving because the teapot is rotating, right? So they're not attached to the teapot. That's what they look like. And there's a good reason for it, because where you see the specular reflections depend on where you're looking at it from. So your view direction becomes very, very important. All right, so let's see how we can handle specular reflections. Again, starting with a plane like this, but I'm going to look at it from side view. So, of course, we have our light source. Light is coming from somewhere, and this is my light direction. But this time, I'm also going to consider the viewing direction. So I'm going to put my camera somewhere, and I'm going to look at that viewing direction. Let's call it V. V is going to be my vector for representing the viewing direction. All right? Now, there are various ways of computing these specular reflections. There are various material models with different types of computing these specular reflections. So we're going to start with one of the simplest materials and one of the first materials used in computer graphics. That's going to be the Phong reflection model, the Phong specular model. Phong specular reflections. Now, this Phong specular reflection model will use the reflection of my light direction. So I'm going to take this vector and I'm going to reflect this vector off of this plane in the perfect reflection direction. And I'm going to call that direction R. So R is the perfect reflection of my light direction. So if this angle is theta, which it is, we call that theta, this angle over here is also going to be theta, right? Because it's reflected. That's how reflection works. Now, Phong's specular model will look at the difference between this perfect reflection direction and my view direction. Now, we said specular reflections are reflections of the light source, right? So if I'm looking at this from the direction R, I should be able to see that light source, right? It's going to be like perfect. But if I'm a little off, it's not going to be, I'm not going to see it as much. It's going to be, maybe I'm not going to see it at all if this is a perfectly flat object. But if it has, and it's perfectly smooth, but if it has some roughness to it, there's some little bit of roughness to it, this reflection is going to be blurred a little bit. So I should still be able to see some reflection from this V direction as well. Right? So this Phong specular reflection model is going to look at the angle between this perfect reflection direction and the viewing direction. And let's call that angle phi. Right? And it's going to look at the cosine of that angle, because cosine is easy to compute, to some power alpha, some exponent alpha. And I'm going to pick that exponent. How I pick that exponent will determine how rough the surface is. If it is perfectly smooth, then I need to pick a very, very large alpha. We'll see some examples. If not, I'm going to pick a smaller alpha value. And how do I compute this cosine? Cosine phi, again, dot product, right? It's going to be the dot product of V and R. Both are unit vectors again, so their dot product will give me the cosine of the angle between them. So this Phong specular reflection model will be based on this term, the angle, the cosine of the angle between these two directions. And of course, I'm going to have some term telling me how shiny the surface is. So let's call it Ks. This is like the specular coefficient of my material. And so these two things, Ks and this alpha exponent, they are going to be my material properties. So they're going to define the kind of material that I'm using for this plane, for this object. Okay? And of course, I need to multiply this by the intensity of the light source, right? Kind of makes sense, just like we did for the diffuse reflection. So multiply the light source intensity by my specular coefficient, and then the cosine of the angle between these two directions to the power alpha. That's going to give my Phong specular reflection term. Alright, so that's how the Phong model works. And if I put this on a material, if I combine this whole thing, the Phong material model is going to look like this. So this is the one that you should recognize. This is the Lambertian model that we talked about earlier, the diffuse model. And this is the Phong specular component. So this material model has a diffuse component and the specular component. So the material has diffuse reflections along with specular reflections, right? So just like the teapot that we looked at, it still has the diffuse wood texture on it. Also has some shiny reflections that are coming from this specular component, right? Now, Ks is a colored value, so that will tell me how much specular reflections I'm going to have. If Ks is black, that is 0, 0, 0, that means I won't have this term, the material will look completely Lambertian. If Ks is some colored value, like it's typically going to be white or some shade of gray. That's typically what it is in most materials. So it's not going to be tinted. It can be tinted in some materials, but oftentimes it's going to be just some gray value. So it's going to tell me the magnitude of the specular reflections. Now this term is going to determine the shape of these specular reflections. And I'm going to show you some examples of that in a little bit. Based on this, I can tell how wide the specular reflections are on the surface. So that's going to control the shape of the specular, and this is going to control the magnitude of the specular reflections. All right. So you see both diffuse and specular terms are multiplied by the light intensity here, so I can just take that light intensity out here. This looks a little more reasonable, right? Okay, now is this something that's bothering you when you look at this equation? Anything bothering you? Because something should be bothering you. Something should be bothering you. So here's the thing. This cosine phi term, I said that's the Phong model. Phong came up with it. and we've been using it as the Phong model. It's okay, right? This is where it came from. Where did this guy come from? Remember this? This is what? The geometry term. Yes, it's the geometry term. And it depends on the geometry of the surface and the light source, right? And it depends on what percentage of the light is received per unit area on the surface. So it doesn't depend on the material property or anything, right? So why is this not impacting my specular term? It kind of should, right? I mean, shouldn't it? It kind of determines how much light I'm receiving on the surface. So it should look more like this, right? I mean, this should be the light. And I should multiply this specular term with that. But no, we don't do that. We don't do that. And there's a reason. Because in the Phong material model, there's actually a hidden 1 over cosine term here. Alright, so that's why we're not doing this. And if you omit this cosine theta, then the Phong model becomes the modified Phong material model. If you don't include that and use this equation that kind of makes sense, you'll get the modified Phong material model. But the Phong material model is going to have this 1 over cosine theta here. Now, if this looks like a hack to you, yeah, kinda, it is a hack, because back when Phong came up with this idea and wrote his material model, he didn't really write it in this form. And we added it later when we realized that, what Phong was doing here in the diffuse term was actually the geometry term. That terminology came to the computer graphics community much later on. So, yeah, I mean, this is a newer form of writing the Phong material model. But this actually makes perfect sense. There's a very good reason why you would have this 1 over cosine theta, which I'm not going to explain, because just explaining that is going to take a very long time. For the time being, just take my word for it that this actually makes sense that you are having a 1 over cosine theta here. And that's how you would get more, I'm going to say, reasonable looking specular reflections that way. I don't want to say realistic, because this is not a physically based model. This is more like a perceptual model. You look at it and you say, oh, most objects kind of look like this, so let me use this term. And that's what Phong did back in 1970 something, and it was good. It still works to some extent. So that's the Phong model. So this is the hidden cosine. So if you Google this, you're not going to find this form of the equation. You're going to find this form of the equation, because for historical reasons, this is what Phong wrote. But I want you to understand that this is the geometry term. Okay? This is not the diffuse term. No. This is not specific to diffuse. All right? This is the geometry term. This tells me how much light is coming to that surface. Right? Actually, this is not even complete, because this cosine theta can be negative, right? I mean, if the light is coming from behind the surface, this cosine theta is going to be negative, which is going to be bad. I don't want that. I mean, what is negative illumination anyway? It makes no sense. So I don't want the negative part. So I'm going to actually write it in this form, right? So when I write it cosine theta, it's shorthand form of this, but this is actually what I mean. If the light is coming from behind, no, I don't want that light. I don't want the negative light. All right, so this has to go. Yeah, this needs to be positive or 0, right? Actually, same goes for this guy. I don't want this to be negative either, because that will make no sense. So let me get rid of that too. Yeah, this has to be positive. I don't want that to be negative as well. Actually, you know what? If the light is coming from behind, I don't want any specular, because that would make no sense. Light is coming from behind the surface, and how would I get specular terms? So, let's take this out over here and divide by cosine theta. So this is actually, implementation-wise, this looks more like it. Okay, so if your cosine theta is negative, then you should say, okay, there's no illumination. Throw it away. Shading is black, nothing. But if it is greater than 0, then you don't have to multiply and then divide by the same number, of course. So you can just, omit this piece and omit multiplication by this as well when you're implementing something like this, right? But, this is the idea. And remember, this cosine theta term is just the dot product between the surface normal and the light direction. And similarly, the cosine phi is the dot product of the perfect reflection direction and the view direction. So the only thing I haven't told you about how to compute this is how to compute this R. Presumably all the others will be given to you, but not R. So let's see how we can compute R. It's not actually fairly easy. I can start with taking that light direction, omega, and just inverting it. If I invert it, it's going to be this guy over here, right? And then I'm gonna go in the surface normal direction from here to there, and for that I will use the projection of omega on the surface normal. And what is this, the length of this? The length of this is going to be, well, if this is 1, because it's a unit vector, if its length is 1, this is going to be cosine theta, right? That this length is going to be cosine theta. So it's going to be omega dot n, and it's in n direction, so I can write it as omega dot n in n direction, surface normal direction. Alright, so I can put one of that over here, that will get me to this point on the surface, and I can add another one that will get me to the perfect reflection direction. So if you combine it all, the perfect reflection direction can be computed by 2 times this guy minus omega, right? So 2 times omega dot n times n minus omega, that's going to give my perfect reflection direction. And we're gonna do stuff like this later on. So it's I think it's good that we talked about this at least once. Alright, now I'm going to show you, now that we talked about all the math stuff is gone, I can show you some examples of what forming material model will look like. Now for these examples, I'm going to start with a very unreasonable example. So here's the unreasonable parameters. My diffuse color is perfectly red, my specular color is perfectly white, and my exponent is 1. So exponent 1 does not make much sense. You see this really reflective, kind of shiny thing. It's a little weird. So let's, I'm going to keep the color values the same, even though these are not great. I mean, if I'm getting this much specular reflections from a realistic surface, this color should be darker. But I don't want to keep it dark, I want to keep it sort of bright, so that's why I pick these values. So these are not going to be very realistic, but you know, it will give you an idea about at least what this exponent does. So let me crank up this exponent to 2. You see that specular reflections became a little narrower, right? And if I crank it up some more to 5, it's going to get smaller to 10, even smaller to 20, even smaller 50, even smaller 100, right? 200. They're getting small. You get the idea, right? 500 to the power 500. It's not a very unreasonable parameter to use for this. Actually, about 1,000. You know what? 10,000, right? So if your surface is really smooth, really smooth, this would be a very reasonable parameter to set for it. Right? Actually, on a perfect mirror, this would be infinity. So 10,000 is a lot smaller than infinity, I would say. By how much? Infinitely smaller than infinity. Alright, so going back to the math, this is our form material model. Now, this is just one material model. Soon after the form material model, Jim Blanton came up with his own material model. It's a little bit different. It's a little bit different in the way that the specular component is computed. So the Blinn material model will not look at the perfect reflection direction. It's going to look at something else. It's going to look at what we call this half angle, H. And that half angle is the angle between this light direction and the view direction. So it's half angle is going to be the direction between these 2 directions. So the angle between omega and H is going to be equal to the angle between H and V. Right? So it's going to be the half angle. So how do I compute this half angle? It's actually very easy. I just add these 2 vectors, V and omega, and normalize it. Just add these 2 vectors, normalize it. That's going to give you a unit vector in the direction of H. And so this is how H is defined. So H is a unit vector exactly between omega and V, the light direction and the view direction. So the Blinn material model is going to use the same equation, but it's going to define this phi differently. Phi is going to be the angle between the surface normal and the half angle. And that's going to be our Blinn material. And of course, I can compute cosine phi by taking the dot product of these 2 vectors, right? So n dot h is going to be cosine phi. So now the foam material makes immediate sense. You'll look at the perfect reflection direction and you're around the perfect reflection direction. This one does not make immediate sense. So let me try to show you a little bit of an intuition of what's happening here. So if you compare the blend and Phong models, so Phong model is looking at this angle over here, right? And the blend model is looking at this angle over here. So if I move my camera, if I take my camera and move it towards the perfect reflection direction, this angle is going to disappear, right? It's going to go to 0, and so will the other angle. So if my view direction is exactly along the perfect reflection direction, then my surface normal and the half vector, they're going to be completely aligned as well. So the angle between them is also going to be 0. But if I move away from it, in this 2D cross-section, the phi angle that the blend model uses is going to be exactly half of the phi angle of the Phong model uses. Right? It's going to be exactly half of it. But that's not the case in 3D. So this is only the case when surface normal, incoming light direction, and the view direction, they all are on the same plane. And they don't have to be on the same plane. They can be on different planes in 3D. If they're on different planes, then this relationship between these two phi definitions is not going to hold. They're going to be different. So what blend does, what blend specular model does, is that it changes the shape of the specular lobe. It's going to take a different shape now than the foam material. So let's see a couple of examples to see what that will look like. Now here's the Phong model, and over there is the blend model. As you can see, yeah, Phong has a larger specular lobe, but it's also sort of like elongated based on the surface direction, right? And this is more circular. So blend would give you a more circular shape than Phong. And blend argued, I believe a lot of people agree, that this is a more realistic looking specular reflection shape. That's more representative of what light actually does. So if I crank up this exponent, both of them will get smaller. Again, they're looking at different angles, so actually like the same, you're not going to get, so if you want to get similar looking specular reflection size with blend and Phong, you should use different alpha values. But I'm using the same alpha value for these two just so that you can see how they differ. This is going to have this sort of elongated shape, and this is again having the circular shape. And you can even see it if I crank it up to 1,000. Over here at 10,000, I'm not sure that you can see, but actually there's a little bit of difference, right? Okay, so this is the blend model and the Phong model, and they all look very similar. There's one thing that's a little bit of a problem for both of them, though. And now we get light, we get shading, only the part of the surface that is facing towards the light source. This other part of the surface, this backside of the sphere here, I'm getting no light. What I mean is I'm getting literally no light, no shading, it's pitch black. And it's not just this point at the back. Anything on the second half of this is going to be pitch black. Like the one hemisphere is getting some light, and the other hemisphere is getting absolutely no light. So it's going to be completely pitch black. So, yeah, in this case, it's not that bad, but what if my background was black? Now my sphere sort of disappeared. I don't even know the backside exists there, right? I can't even see it at all. I don't even see the shape of my model anymore. So this is a little bit of a problem because that's not quite what happens in reality. In reality, there's always light coming from all directions in some ways. And we're going to talk about that We're going to talk about how to compute that, but computing that is actually very, very expensive, very, very hard. Back in the 70s, it was really, really expensive. Even today, it's very expensive. Back in the 70s, it was like, whoa, we can't even think about doing that. So they came up with this very simple idea. It's still used today. The idea is having some ambient light. Just have some light around coming from all directions. This ambient light term. And that ambient light term is going to add some light to everywhere. And if you add some light to everywhere, you're going to start seeing something on the surface. Right? Now, if I add some ambient light, I can see that, oh, this was a sphere. Right? It's not completely lost in the blackness of my background. It's actually visible now. So it solves that problem. So things are not sort of unrealistically dark, like pitch black dark. And I can control how much ambient light I want in my scene. And if I put it inside my Blinn Phong material model, I'm going to have the diffuse term, I'm going to have the specular term, and I'm going to have this ambient term here. Now, in this case, I have this ambient color of my material as a parameter, just multiplied by the ambient light. So this IA is different than this I. This I was my light source. IA is just some ambient light defined independently. All right, and this is my ambient coefficient of my material. Now this looks a little funny. All right. I think you guys understand where this ambient light is coming from. It's actually not coming from anywhere realistic. It's just coming from a necessity that I want to have some lights everywhere, right? I don't want anything to be pitch black because that's not very realistic. So it's a very, very crude approximation of light coming from all directions in more realistic scenes. But where's this ambient material terms coming from? This is a little strange to have an ambient material color. Like what? I mean, you can understand, like this is the color of the surface, diffuse color is the color of the surface. This is the reflections of the light source, right? The specular reflections. I mean, I can understand what these are. This is like if I have a wood texture, that's going to be this wood texture, right? And if this is going to be just how shiny that is on the surface. And this is going to be the shape of that shininess, how smooth the surface is. But what is this? It doesn't make any sense to have an ambient color term here for my material. So most of the time, even though it's a material term, I'm going to say that my ambient color is going to be the same as my diffuse color. Most of the time, the typical thing to do is to say that they're the same. They don't have to be. A lot of software will allow you to specify this color independently, just to give artists a little more control. So if you see this, don't be surprised. It's actually exposed to the end user so that you can actually control it. But most of the time, what makes sense here would be to use the diffuse color as your ambient color. Right? So if it's not given to you, you would use a diffuse color. Okay, and that's exactly what we're going to do in the project. All right, so this is shading using Blinn and Phong model. Now, when people talk about the Blinn Phong model, they sometimes call Blinn model Blinn Phong model. They're talking about the Blinn model. I'm saying Blinn / Phong material model because it's the same equation. The only difference is how I define this angle phi. That's the only difference between these two material models. Okay, that's all I had in mind about computing shading. In our remainder of our time, I would like to briefly talk about how to handle light sources in computer graphics. There are various ways of handling light sources in computer graphics. So I'm just going to briefly talk about this. I'm not going to go into a lot of detail over here. This can be a very, very extensive topic on its own, but I don't think it's too fundamental. It's important that we get the basics, and so I'm just going to cover the basics here. There are various different light types that we can define, we use in computer graphics. Here's some illustrations of different lights on the sphere and what they look like on the sphere and on the walls and on the ground with shadows and everything. The simplest one that you can think of, and the one that we're going to be using in our upcoming project, is the directional light. So directional light the example is far at the end over there. The directional light is going to have, just a very simple, it's going to have a light intensity and direction. So it's light coming from said direction, whatever that is. That's going to be the directional light source. Very, very simple. It's actually a pretty decent approximation of a light source like the sun. So sun is far, far away. So for all intensive purposes, you can assume that sunlight is coming from just one direction. Right? You set the direction for your scene. It's always coming from the same direction. Yeah, there's a little bit of a variance depending on where you are at any point. There's going to be slightly different because sun is not coming from the same direction everywhere on Earth at the same time, right? But since our scenes oftentimes are much smaller than the Earth's surface itself, it's a good approximation. And it's okay. So directional lights are actually used fairly often, and they're often used as a replacement for a light source like the sun. The other one is going to be points or a spotlight source. A point light source is just a point that emits light. It's one of the simplest light forms used in computer graphics. Because of its simplicity, actually point lights are used a lot. They're very, very popular even today. Not the most realistic light sources because they're just a point, and a point does not have a size of anything. So, I mean, realistic objects have sizes. Points don't have a size. So, so in that sense, they're not very realistic, but they are a good replacement for small light sources. If you have a small light bulb somewhere. So what does small mean? Small in the context of your scene, right? I'm rendering a giant hole and there's some light source up on the ceiling. Maybe it could be a point light because it's very small as compared to the rest of my scene, so I might as well just approximate it as a point light, and that would be fine. Right? So point lights are used a lot. The other variant of that is spotlight. Spotlight is a point light that doesn't just, unlike point lights that eliminates all directions, just emit light in all directions, spotlights will emit light in certain directions only. So there's going to be a spot angle, and a spotlight will send illumination only along that direction. So as you can see, over here, the point light example is illuminating the wall really nicely because it's illuminating all directions. But in this case, the spotlight, it's very much like a point light with a spot angle around it. It's not directly illuminating the wall, illuminating the wall, but not everywhere, right? So it's illuminating only a part of the wall that is contained in that spot direction, right? So that's a spotlight. Of course, it will come with additional properties. So a point light is going to have intensity and position. So if you want to know the light direction, you're going to have to compute it. So there's this point A in my scene in 3D, and I want to know where the light is coming from what direction. I am just going to have to compute the vector from this point towards the light position, and that's going to be my light direction, right? So for any point in the scene, I'm going to have to compute the light direction if I'm using point light sources. If I'm using a directional light source, I already know my light direction. It's a parameter of my light source. So it's already given to me. But for point lights, I need to compute it. Same goes for spotlights. In addition to being a point light, I need to check whether that direction is inside this spot angle. If it's outside that spot angle, I'm going to say, okay, no light is coming. If it is inside, then I'm going to say some light is coming. So those are the simpler light sources we have in computer graphics. The other more realistic light sources, that are more modern light sources that we use more often in especially for offline high quality rendering, and also some in high quality real-time rendering, is going to be area light sources. Now these are more realistic because these area light sources will be a much better representation of objects that have some size. Think about area light sources as like surfaces. Objects in reality are volumetric, but we represent them in computer graphics as surfaces, right? Same goes for light sources. Light sources have their own volumes, right? There are sizes and masses, but we represent them as their surface areas. So when we say area light source, don't say like it's a flat. It doesn't have to be flat. It can be flat, like a rectangle light source or disk light source, or it can be a sphere, or it can be some arbitrary polygonal mesh. I can say teapot, my teapot is a light source. It can be a light source, and you can use it as a light source, and that'll be perfectly fine. But now, how do you compute the light direction from an area light source? Now that's going to be a little tricky, right? Because, okay, for directional light source, it was already given. For point light source, I could just compute the direction. For an area light source, I don't have just one direction now. Now I have like a range of directions that correspond to that area. And so that's going to be a bit tricky. So computing area light sources, working with area light sources, is going to be computationally a lot more expensive. For some specific cases, there are ways to sort of compute it relatively efficiently. But in general, computing lighting from area light sources is going to be a bit more tricky. And also, doing shading with area light sources is going to be tricky, right? Because with shading, I need to know the incoming light direction. But if my light direction is a range of directions, like how do I do blend shading now? It's not going to be that easy, right? I kind of need to look at an integral over a surface or something. Yeah, that's literally what we're going to have to do. That's literally how it works. And there are different ways of computing that integral. We're going to talk about a part of it later on. But for now, just know that these are more realistic light sources, area light sources, and they do exist, and they're very, very helpful, and they're going to be a lot more expensive to compute. The final type of light source that I'm going to talk about, that's not given as an example down here, is going to be a skylight or an environment light. Imagine that you're in a sunny day. There's sunlight, of course. Sunlight is the dominant light source, and maybe I can approximate it as a directional light like this. But there's also light coming from around me, from the atmosphere. And that type of light can be represented using what we call a skylight or an environment light. So that's going to be the light coming from all directions. It's not coming from specific objects per se, like this mesh light. It's coming from directions that are far, far away, going all the way to infinity. And they're coming from all directions. They may be the same amount, so I can have a skylight with a constant color value. In that case, I'm basically saying I have this constant light coming from all directions that you can think of. I have the same light coming. That's going to be a constant skylight. But oftentimes, I'm going to use some function to determine the amount of light coming from all directions. So given a direction, I'm going to compute the amount of light coming from that direction. I can have some procedural function for that, or I can just use a texture. I can just use a texture image. And that image tells me how much light is coming from all directions. Like imagine like a giant sphere encapsulating my entire scene. That sphere's radius is infinity. Quite literally, infinity. And my scene is centered on that infinite sphere. And I have a texture on that infinite sphere that will tell me how much light is coming from all directions. So that's going to be a skylight or an environment light. And I can use that environment light also as the background. So my camera is looking in some direction. Whatever I see as the environment light could be the background of my camera image. And this brings us to the concept of image-based lighting. So I can take an image. I can actually even take an image of an actual scene, and I can use this as an environment image. I can form like a 360 environment image of a scene, and I can use that for doing lighting. They use that a lot for special effects with live action, actually. So in a set, they would take the lighting measurement coming from all directions. So when you put a virtual object in that scene, it can be illuminated by the same illumination environment that exists in that scene. And that's the concept there is the image-based lighting. So here are some Here's an example of image-based lighting using a sphere, using 3 spheres with 3 different materials on them. So as you can see, we have some very nice reflections of the light source. That's the environment light. That's basically the environment image. And we're getting some super nice shadows underneath that down there. And if you look at this white sphere, you see that some color variations, color sort of changes. It's very subtle. But these kind of subtle differences is what actually sells this image and what makes it look realistic when you look at something like this. So image-based lighting is a very, very powerful tool for generating realistic images. Of course, there's a lot more that has to get into generating an image like this. You need to have realistic material models. I'm not sure what material models these use, but if they're not blend foam, I'm not going to be surprised. So the image-based lighting is just one component of getting this realistic looking image. There's going to be other components there as well. But talking about lighting, I talk about image-based lighting as well. But most of the time what we're going to be concerned with is going to be just point lights and directional light sources in this course. All right, because those are simpler light sources. All right, so that's what I plan to cover for today. Just one thing that I realize I haven't specifically told you. What happens if you have multiple light sources in a scene? Let's say I have 2 light sources and I'm going to do blend shading. How am I going to do that? I have light source A, I have light source B. Which one am I going to use? Am I going to use both of them? And if I'm going to use both of them, well, I should probably use both of them. How am I going to combine them? Am I going to take the average light intensity, or am I going to take the average direction? So something like blended light source? No, that's not how light works. Light is additive. All right, so you compute the reflections from one light source. That includes diffuse reflections and specular reflections. And then you compute reflections off of the other second light source and you add them on top of it. If you have a third light source, you add that one too. If you have a fourth light source, you add that one too. Just like we added the ambient light source, right? We added the ambient light on top of the diffuse and specular. Just like that, for any lights, you're going to have the diffuse and specular components and you will add them on top of the other light sources. Right? So it is additive. Keep that in mind when you're dealing with multiple light sources. But luckily, in the upcoming project, we're going to be dealing with a single light source. So that's going to be a little bit easier. Not a lot easier, just a little bit easier. Alright, so I'll end it here then. Thank you all for sticking around till the end. Your slides, Brian. Thank you. I'm happy that you like them. I'll have more coming next time. Alright, thank you all. I'll see you all next time.